Right, so it's now 3 o'clock. Welcome here to RISE Learning Machines seminars. RISE is Sweden's state-owned research institute with nearly 3,000 researchers working at 35 different locations all over Sweden on research areas spanning from bioeconomy to material science, transport, and digital systems. Our weekly learning machine seminars are organized as part of our Center for Applied AI Research, which connects researchers working on topics such as natural language processing and state-of-the-art machine learning for applications such as environmental modeling and industrial applications. Today, I have the pleasure to introduce Sofia Broomé, who is a final year PhD candidate at KTH under supervision by Hedvig Källström. Sofia has been working on video modeling, such as action recognition, and modeling sensor data, such as inertial measurement units. Today, we'll hear about equine pain behavior, horses, that is, and a study of spatiotemporal features learned in video classification models. Also, I happen to know that tomorrow, Sofia will defend her PhD thesis with the title Learning Spatiotemporal Features in Low Data and Fine-Grained Action Recognition with an Application to Equine Pain Behavior. So with that said, I hope that we'll get a really nice sneak peek of some of the results here today. So with that, please, Sofia, the floor is yours.
Thank you so much, Olof, for the nice introduction. Do you see a starting slide now?
Yes.
Wonderful. All right, so welcome everybody to this talk on horses, pain, and time, which, where I'll give you an overview of my research as it's presented in my thesis, which, as Olof said, I'm actually defending tomorrow. So except for some details, this is a little bit of a rehearsal for that, so you get to hear it first. So broadly, my research lies in both the union and the intersection of these two fields of computer vision for animals on the one hand, and video understanding on the other hand. And these two are united by the fact that I've been using and exploring deep learning methods within both, but also because one important argument that I've been wanting to make in the thesis is that using temporal context is important when studying animal behavior in computer vision. So I'll first go over some background for the application, as well as our results on equine pain recognition, and then move to talk about how we learn spatiotemporal features in deep video models more broadly, and the conceptual importance of three different types of temporal modeling and for video, and partly in how they relate to biological vision as well. And then these hypotheses from part 3 are explored more empirically in the fourth part, and then I'll share my conclusions and recommend directions for future work. And I should also add that you're super welcome to interrupt me at any point. That's just nice for me to have some input, actually, if you're confused by something or have other questions. So yeah, and just breaking, unfortunately, I don't really see any Zoom things now, so just hop in with your voice in that case.
I will also keep an eye on the chat. So. Yeah,
super. Okay, so yeah, exactly. If there's a written question, you can also interrupt me. Thank you. Okay, but so why is it that we want to recognize pain in horses, actually? Well, pain is a manifestation of disease. So if we can learn to recognize it, we can increase horse welfare. And in Sweden, one of the most common causes for culling horses or euthanizing horses are orthopedic disorders like arthritis. So problems with joints, which aren't lethal. So if we could detect pain earlier, we'd have much better chances of treating these horses. And then there's a lot of controversy existing about the nature of pain. And there's a subjective difference, or there's a difference between nociception, which is the sensory nervous system's response to harmful stimuli on the one hand, and our actual subjective experience of pain on the other hand. And humans have grimaces that we can make to express pain that occur already for infants. And for horses as well, facial expressions have been identified that are associated with pain, but neither for humans nor for animals is there a single known behavioral or physiological parameter that says that pain is present without a doubt. But there are a number of challenges when it comes to recognizing pain in horses. And from the machine learning perspective, we haven't come as far in action recognition as we have for single image tasks. And recognizing actions from different viewpoints and with variations in background, which is easy for humans, is still very difficult for neural networks. And we can compare that to, for example, object recognition in single images, which in some cases has surpassed human abilities. And then there's an additional challenging layer here on top of that, which is to not only recognize if somebody is performing a certain action, jumping, but also the underlying emotion of that action. And horses are a non-verbal species, so they can't explain or signal their pain in words to us, as you know. And another layer for this problem is that horses are prey animals, and they tend to hide their pain because they don't want to be seen as vulnerable. And to show you that pain recognition in animals is quite a young field, here is actually a comprehensive overview of all the papers or academic works attempting to recognize pain in animals from vision data using ML. So, and it's around 10 works, as you see. And here I also wanted to show how most approaches have been made on single image data, as you see to the left in the slide. And another point I wanted to make here is that by now, the majority of the works use deep learning, but you find some traditional handcrafted methods to the left also. And I'm happy to say, let's see if we can, is it a pen pointer options? No, or maybe you see my, well, yeah, So I'm happy to say that there's now a work from the University of Utrecht on pain recognition in dogs, which uses video and which builds on my method for horses, but also incorporates pose information. So my hope for the future is that it will be increasingly common to use the temporal dimension for these types of tasks. So these 4 boxes represent the 4 articles that my thesis is based on. And in the first one, I could confirm that pain recognition improved when I used deep learning models with stronger temporal modeling. And using that type of models made me think about how we can interpret the decisions of deep video networks, which had been explored very little then. So that led to the second work. And in the third paper, I'd received a new horse pain dataset, which was difficult to train on because the horses weren't that much in pain and the labels were very noisy. But we found that we can use knowledge from a cleaner source dataset to classify this noisy data. And we also found that the generalization ability between the 2 pain types in this paper could vary between different types of video models. And that last bit led me to the 4th paper, where I compare 3 principally different methods for temporal modeling on how well they generalize to new domains. So with that, I'll now move to present our horse pain recognition findings. So papers 1 and 3 in this figure. Right, so my first article was a classification approach to recognizing pain using deep learning, where I compared architectures that vary in how much they model the temporal dimension of the videos. And these were then compared to a human expert baseline, which we outperformed on this particular task. And we were also the first to perform pain recognition on animals from video. And the first to do an investigation of what role motion and temporal information plays in this kind of problem. And this picture summarizes the results from the article. And we see that the conval SDM to the far right in its two-stream version, you do see a little bit of a mouse pointer here when it moves, it is. Right?
Yes, we see it.
Oh, thank you. Yeah, so the conval SDM was the best candidate here for the task. We can see that the veterinary classification results are a lot lower than ours, which says something about the difficulty of this task. And it should be noted, though, that this is for the task of classifying a single 5-second clip without context. And in their work, veterinarians, of course, have access to the clinical history of the animal and other physiological factors. But even so, a routine check at a horse hospital can sometimes be around 5 seconds, according to veterinarians I've collaborated with. And so for each of these models, these 3 models, we try to give either only RGB or only optical flow as input, and those are the blue and purple staples. And we can see that the gaps between the flow and the RGB versions are bigger for the inception model and the BGG LSTM model, but it's the smallest for the conval SDM. And the conval SDM is also the only one that improves with 2 streams. So this says, or indicates that the conval SDM can make better use of motion information than the other 2, and temporal information seems to be important for this.
Questions there?
Yes, please.
Could you describe a little bit about what optical flow is and perhaps also what 2-stream is?
Of course, yes. So optical flow is a way to measure how pixels have moved between 2 frames in video. So you take frames that are sampled with quite high frame rate, like I have 16 frames per second in this case, but it can be in the natural frame rate, like 25 or 30 frames per second. You take the 2 adjacent frames, and then there's an algorithm to compute how the pixels have moved. It's like a bit of a derivative in the X and Y direction of how pixels have moved. I think, well, we had one example. If you see here, that's an example of optical flow data. So in that case, the head is moving in some direction there. And then 2 streams in the context of a neural network. That's from a paper that was introduced in 2014 for video classification in particular, where the classical setup is that you have one network with RGB frames, so just normal video data that comes in as input. And then you have a parallel network that takes optical flow as input. And you train this jointly, and then you merge them at some point, their output. In my case, I add the outputs from the 2 streams together later on. So it stacks the information from both. Is that sort of clear for now? Can come back to it also.
Yes, thank you.
Thank you. All right, and then last we can say that it's important to have efficient models since we don't want to collect so much pain data for ethical reasons. And the conval SDM, as you see here, has orders of magnitude fewer parameters than the 2 other ones, actually. So that's a good thing. Here I compare the 2 best models in the study qualitatively, and so they're quite near each other in average accuracy, but I wanted to investigate what they were actually looking at. And this was done using GradCam visualizations, which GradCam heat maps show what a certain model has focused on for its classification decision. And we see that the conv-LSTM model in 2 streams has a more temporally smooth focus pattern than this one, the VGG-LSTM, where the focus of the VGG-LSTM jumps around between the frames and sometimes looks at irrelevant information. Whereas the conv-LSTM observes things that are believed to be relevant for the pain expression, like the neck posture and also the sort of tense eyes here at the end of the sequence. And it sticks to these, which gives us more confidence in the model. And so these were only qualitative studies of some examples, but they indicated that there might be a difference in what different video models look at in the data. And that makes me realize that maybe I should clarify, when I say a video model, it's really essentially a neural network, but that takes a sequence of images as input, and then it has some manner of sewing these frames together inside the network, and that's what I mean by temporal modeling. Yeah.
Do you have a diagram or something about over these models?
Not as part of this presentation, but I think in some of the bonus slides at the end. Well, we had this little one also.
Is there any difference in how the VGG plus LSTM handles the recurrence as compared to this?
Yeah.
And combinant.
Exactly, there's an important difference, and it's a bit silly that that's not part of this presentation. It's for time reasons, so that's an important question. And the VGG-LSTM, that's essentially a 2D CNN, so a normal single image network first, where you let all the frames of a sequence go through that one, and then you model, then you put an RNN on top of that, then you need to flatten whatever output you have for each of the frames, whatever CNN representation you have of the frames, you flatten that so you don't have any spatial structure, and then you feed it to the LSTM, which is just like a classical type of RNN or LSTM. And but for the conv-LSTM, the thing about that one is that it replaces matrix multiplication in the LSTM equations with convolution, which lets it have a spatial structure within the recurrence. So they are really different. And the big thing about the VGG-LSTM is that it separates the spatial from the temporal modeling completely, whereas this one models the temporal and spatial dependencies at the same time. So it's recurrent throughout the whole model, whereas the VGG first does a spatial downsampling and then does a temporal.
Right, thanks.
Thank you. Okay, but continuing on the horse pain theme, in this next one, we explored pain domain transfer. And the contributions of this paper are that we did the first experiments on domain transfer between different types of pain in animals. And we also put emphasis on the difficulties when you move outside of the benchmarking realm in action recognition and need to work with sort of real-world dirty data sets. And we present an explainability study comparing 27 Swedish horse veterinarians to the best performing model. And then, I should also say that it's an interdisciplinary paper that also discusses the biological differences between the two pain types and whether it's realistic that they can transfer from each other. To give you a little bit of an overview of the 2 horse data sets that I've been working on in the thesis. We have the pain phase dataset used in paper 1 here to the left, which shows sort of clean and experimental acute pain, which is a good and clear model for pain used in humans as well, but it's less clinically relevant, you could say. And the pain induction methods here are either a blood pressure cuff around one of the limbs, or capsaicin extract on the skin, and that's a kind of chili cream, and they're both applied during 20 minutes. And so then the labels in this data set come from whether the trial was on or off. And then for the new and noisy data set in this paper, what we have is really mild orthopedic pain, so pain in a leg, which comes from an injection of lipopolysaccharides, which creates an inflammation in the joint with an individual peak after several hours. And the labels from this data set actually come from pain scorings by human experts standing live by the horse before the horse is actually filmed. So nobody watched and labeled the actual videos. And then these pain scores are then binarized with a threshold at 0. So when I said that we're in the previous paper, we're really training in a very standard supervised manner. We put in a video and then we have a label that's pain or no pain for it that we use gradient descent. And the experiments of this paper contain 3 parts where we attempt to perform standard supervised training within one domain first, which turns out to be difficult for the orthopedic pain dataset. And then we try to run weekly supervised learning, which turns out to be difficult as well, as you'll hear about. And then domain transfer from the cleaner dataset to the left there turns out to be the functioning method. And last, we compare the classification decisions of the 27 veterinarians to the best performing model. So starting with the standard supervised training. So in these experiments, we're again comparing the 2-stream conval-STM that we saw in the last paper. And now also a state-of-the-art 3D CNN, so a CNN that can take video input called the i3D. And what we see is that when we train only on PF, they both achieve quite good results, but not when they train only on this orthopedic pain dataset, EOP. And we then thought that we could combine the 2 datasets and thereby doubling the size. So we tried that, and it first looks like an improvement. But if you break down the results, it's actually deteriorated for the PF horses. We always separate, so we test on a singled out horse. So we have results for one entire horse, so that the model has never seen the subject. It's validated and tested on. For the i3D, it actually got worse for EOP in this double data set. The conval-STM got slightly better on EOP, but not still not good enough. So we observed that it seems difficult to train only on this EOP data, and doubling the data set by mixing the 2 domains doesn't help. So what should we try instead? Well, we look then at standard methods for weekly supervised learning in action recognition, where you typically have a multiple instance learning objective and treat one video, which can be around 5 minutes in my case, as a bag of little clips of maybe 5 seconds each. And then you'd look for positive examples in that bag. So if you find a certain number of positive pain clips, you can classify the whole video as positive in terms of pain, for example. And we call this the sparse pain hypothesis for orthopedic pain, in that the pain behavior would appear only sporadically. And a typical setting that you have in weekly supervised action recognition is that you have noisy labels, but you have a large number of samples, which can eventually allow you to learn even quite a weak signal. But in our case, we have very noisy labels, but we only have a small number of samples, only around 100 of those 5-minute videos. And multiple instance learning is not stable in that case. I sort of painstakingly found out after many experiments. And essentially the results were not above random here. Right, so instead we decided to train a model on the entire PF dataset, so the clean one, and then either fine-tune on the EOP dataset or just test simply on the completely unseen EOP dataset. And it turns out that the recurrent model, Conceptual, then achieved 58 actually on the entire EOP dataset, which was higher than any other approach so far. And the I3D, this big 3D CNN, did not generalize as well, even if they came from similar results on the source dataset in PF. And then we can mention that we also see quite some individual variation between subjects, which are in the columns here, so Aslan and Brava and the gang. Also we saw that fine-tuning did not work well, which is natural because the labels on EOP are just too weak to train on in a standard manner. And then using this best performing recurrent model, the Conceptual, that's been trained only on the PF dataset, so it's never seen this orthopedic pain horses. We compared it to these 27 veterinarians who got to rate 25 clips, 5 seconds each for pain. And these 25 clips used here were selected with a pain score that was above 1. So we had a slightly bigger margin there between no pain and pain. And they were also without occlusion. So it's slightly easier than when evaluating on the entire dataset, which is third year. And then we see that, so this is the model to the right. The model actually performs better than the experts here. And specifically, the humans tended to overclassify clips as pain. And as I said, these 25 clips have a clearer margin between pain and no pain. So the model is really better on these 25 clips. It has 76% F1 score here compared to on the entire dataset where it had 58, as you saw. And to look into this comparison in more detail, we listed a number of behaviors that might appear in these clips. So from this list, we made a catalog for every clip, what they contain. And then we studied what the humans tended to think of as pain and what the computer, on the other hand, tended to prefer. So here you see the confidence of the model for every classification and what label it shows. Right. And what we saw studying that big table is that clips that were rated as less painful by the humans, they tended to contain fewer of the classical pain behaviors. Now I actually, now I got the notification for the chat. Hi, Richard. So how do we know that the humans mistakenly classified pain? So the humans, they got to rate, well, we have ground truths for the horses.
Sorry, maybe I should have asked, how do we know ground truth?
Right, it's so we have films when the horses are just normal and not under pain induction, and then we have films when they are under pain induction. So
yes, of course, yeah, right.
Yeah, no, but it's a strange thing at all. But that's how it works. So this lipopolysaccharide like inflammation injection that I was talking about, that's when we know that those films are taken after that injection. Basically. And then these scores come from 3 human experts who have watched the horse and said according to pain scales that the horses are under pain.
Perfect. Thanks.
Thank you. So yeah, the humans they tended to look for these classical pain behaviors, and that's, for example, we have clip 6 here, which is a pain clip, which does not have any of the classical, these are the classical ones, pain scores, or any at all actually. And then the average rating between 0 and 10 is 0.96 here, and only half of them were correct there. So it's quite low for them. Then we can say that clip 6 here, that's the one we saw. So it's rated very low for the humans, and the model is correct here actually. It says pain, but it has very low confidence, 0.52. And then we have 3 clips with clear movement in the list, where 2 of the pain clips are wrongly classified as non-pain. And then we have 1 non-pain that's correct with very high confidence. So the model, the computer here seems to associate movement with sort of healthiness and non-pain. And some more observations are that the 4 most confident and correct non-pain predictions, so above 0.99 confidence, they happen precisely when the horse holds his head very upright among the non-pain clips. And then out of the 3 incorrect pain predictions, 2 of those contain the only non-pain clips with a lowered head, which the model seems to associate with pain. So both of these show that the model seems to focus on head position. And then the 3 most confident and correct pain predictions by the model all contain some ear behavior. And here the model and the humans are both quite confident about the presence of pain, and ears are a classical sign to look for. Right, so now we've seen the 2 horse articles, and to conclude for this part, we've seen the first attempts at recognizing pain in horses, and we made the choice to learn the data end-to-end from pixels. And in that choice, these studies also become commentary on deep learning and its limits, and what different models tend to pick up on from the raw pixels. And we've also seen that the temporal dimension is important, and that the choice of the video-based architecture can matter for generalization. And so this opens up for a broader discussion on how to model time in video. So which brings us to this little interlude between the horse and video parts. But so some questions that we take with us from the horse part are, does temporal modeling matter for the types of features we learn, actually? And in particular, does it matter for generalization? And one fundamental aspect of seeing is being able to recognize from one moment to the next what objects or shapes remain the same. And we can refer to this ability as temporal coherence, where temporal coherence saves us brain computation, and we don't need to recognize faces over and over again while they're in our line of sight. And we keep a memory buffer that continuously informs us about what has or hasn't changed about the scene. And so we use temporal information as we go about this. And for these reasons, I argue that we can't have a practically functioning visual system without temporal dependencies. But as you know, computer vision in the deep learning era has largely been focused on single image tasks. And one reason for that is, of course, that it's more computationally heavy to run on video input. Another reason could be that the publication culture during the 2010s and still within deep learning has been to present state-of-the-art results on benchmarking datasets. And it seems as though it's been more rewarding to directly optimize methods to the datasets than to think broadly and potentially slowly about how to best achieve generalizing models. So a fast pace has characterized a lot of the computer vision research. And in my view, video data can teach us in abundance that everything about vision pretty much, that this slightly deformed shape is the same entity as the one in the previous frame. And for that reason, in theory, spatiotemporal features have the possibility to become very powerful visual descriptors, even for static visual scenes. And this is where I think the field of computer vision should be headed. And now to show you some important conceptual differences in temporal modeling, I've drawn this schematic image of 3D convolutions and self-attention and recurrence across frames in a video, where a 3D CNN will treat time as a third spatial dimension, and it convolves, which is a linear operation across small tubes in the video, where the temporal order doesn't matter. So all nonlinearities appear instead between the successive layers, instead of between time steps. Whereas a video transformer will use self-attention between the frames as temporal dependence. And this means that we've now introduced nonlinearities between the time steps, but the time is still symmetric in that the attention represents the mutual relevance between elements in a sequence, no matter where in the sequence they appear. A recurrent video model, on the other hand, also has nonlinearities between each time step, but it importantly models time in the forward or in the causal direction, which is the most physically correct way to model time. And so a hidden state at t does not have access to information at t+1. But recurrence in video models is becoming more and more rare, and they're slow to train because GPU hardware is most optimal for parallel rather than sequential models. And at the same time, experiments in psychophysics have shown that feedback connectivity is really important for more complicated visual tasks. And this can, for example, be done using backward masking, where a noise mask is presented short after a visual stimulus, which will block the interaction between the recurrent signal and the input. And it's been found that for simple tasks, this doesn't really affect them, but for more difficult ones like pattern completions, those are effective. And the RNNs are simply more efficient and compressed in terms of wiring, and they can achieve arbitrary computational depth on finite spatial components. So this image shows the feed-forward on-roll equivalent of an RNN, and as you see, it takes up more space, which matters for brains since we need to carry them around, and it matters for computational hardware implementing computer vision too, since space and material costs are finite there too, not least for portable applications. And then RNNs can adapt their energy usage to the task at hand, whereas a feed-forward model always has a fixed number of steps between input and output. So with recurrence, you can prioritize sensory computation based on the urgency of the input. And there are some recent reviews in neuroscience that have pointed to this large discrepancy between brains and computers. How the computer vision models are dominated by feed-forward models, and brains are instead have abundant recurrence. And given that the tasks that have been given a lot of importance within computer vision, like classification or segmentation, are quite simple tasks, it's maybe not surprising that they have been dominant. And the problems start when the models either need to perform more complicated tasks or learn how to truly generalize across different domains. So now going to the video part of the thesis. I see that it's 3:40, but yeah, well, I might skip some things. So this article from 2020 is the first empirical study comparing what kinds of features that 3D CNNs and convolutional LSTMs learn. And it also introduces an explainability tool for video. And we were able to show quite consistent differences between the 3D CNN and the convolutional LSTM in what they learn. And on average, the I3D tended to have shorter temporal masks, so for what it focused on. And the I3Ds tended to focus on a single region or fewer regions in the image, in the sequences. And these regions were generally also larger than for the convolutional LSTM, and they tended to be biased toward the middle of the image. And for this dataset, something, it's called, it's important to note that focusing in the middle of the images is a smart choice, since most of the action really does happen in the middle of the frames. So likely these trends have come up because I3D is an efficient learner that figures out what the smartest way to solve the dataset is. But on the other hand, this might not be the way that generalizes the best in the wild. And then we could see that the convolutional LSTM was also more sensitive to the temporal order of the frames when we reversed these masks. Yeah, of course, looking over a lot of details there. So, moving to the last paper, here we looked directly at generalization for the first time. And we compared 3D CNNs, video transformers, and recurrent models on how well they generalize. And we extended the notions of shape and texture bias from this iClear 19 paper that you see over here to video models. And then we presented 2 new public datasets to investigate domain shift for video models and temporal models. And one of those datasets is called temporal shape, which is a task of trajectory classification. So one frame doesn't matter here. And we have, it's a 5-class classification task where the classes are circle, spiral, arc, line, or rectangle. And what we see here are examples of the circle class. And this is across 4 domains. So we have a 2-pixel dot first, 2 dot, and then a 5-pixel dot, and then a random NIST digit, and then a random NIST digit with a Perlin noise background. And what we do throughout the paper is to train and validate within one domain, and then take the best model from the validation and see how well it performs on the other unseen ones. And that will be the same for the diving Fourier experiments also. And we then measure how robust they are across the domains, see if they've learned sort of the true task and can carry that out. And this dataset does not contain any appearance bias or frame bias. So here we rather evaluate the sort of pure ability of temporal modeling. So, right. So what we study, as I said, in these experiments is the ability of temporal modeling in the absence of spatial or texture bias. And when we train on the small dot and compare how it drops to the other domains, we found that the green and blue curves, convolutional LSTM and the timesformer, are the most flat ones and thus the most robust across the domains. But when we train on NIST with background, it's the larger video transformer, the timesformer, that's the most robust, it's the dark blue one. And a video transformer, like the timesformer, really has an excellent ability to learn long-term dependencies, both spatially and temporally, which is why we believe that it could learn so well to disregard this Perlin noise in the training set when the data is free of appearance bias, as it is here. But we'll, however, see later that a downside to the video transformer is that it is more prone to encode texture bias when that's present in the data. But essentially, the convolved YAML and transformer were the ones that seemed more robust here. Then we also looked at how this robustness changed with model size across different domains. And in the nearest domain, so we've still trained on this little dot, and then we go to this nearest one with a slightly larger dot, we see that the red and blue curves of the 3D CNN and the transformer, the trend for them is upward with a larger model size and on the x-axis, which is number of hidden units per layer. But as we move further from the home domain to the NIST one and the NIST with background, model size ceases to help here for those two models. So good results with large models in one domain for the 3D CNN and the transformer can potentially be deceiving in terms of performance if we find ourselves in a situation with more domain shift. And these are our modified domains of Diving 48, which is a common dataset for fine-grained action recognition where motion and temporal information really matters. And it has 48 diving classes, and so random performance is about 2% here. So the task is to recognize different dives. And we've made these two, what we call shape domains, where we've segmented out the class evidence. And then we have this cheating domain where we see only the background. And we call that the texture domain, so that there's no class evidence in the two videos. And for this experiment, we also look at how models drop on completely unseen domains. So the models are always trained on only the original data, and then we see how they can tolerate the modified ones. And here are some examples of results where we control for layer structure for the three models. And they all have 4 layers with 128 units each. And they also have the same exact performance on the validation set. And what we see then is that the blue and red, so the 3D CNN and the transformer, they actually increase their results slightly on the texture domain compared to S1 and S2, whereas the convolved YAML always decreases for T, which is the desirable behavior because ideally it should just be 0. Another example experiment here is with the best versions of the models after hyperparameter search and with the performance kept fixed at 50% accuracy. And we see that the two models drop similarly for S1 and S2, but that there's an important gap between the 3D CNN and the convolved YAML on the texture domain. We also looked at some qualitative examples here, and to prepare for this, we can note that every class in Diving 48 has 4 attributes, which is about how the diver starts, so the takeoff, how many somersaults they do in the air, whether they twist or not, and what their flight position is. So each of the 48 classes are defined according to these 4 attributes. And then what we did was to look at the misclassifications for random clips and classes. And we found that among the misclassifications extracted as a set here, the convolved YAML for each random class that we looked at had the most correct attributes among the misclassifications. So it looks like it focuses on more relevant patterns for the task than the other models. So what we saw in this study were indications that recurrence for temporal modeling helps with cross-domain robustness, and that the convolved YAML exhibited less texture bias than the 3D CNN and the transformer. And what we draw from this is that the temporal modeling in base architectures can matter for high-level behavior, and that there's a point to revisiting the fundamental architectures of the models rather than always adding advanced superstructures or sophisticated training schemes to the models to cure their symptoms on poor generalization. And how to model frame dependency in video is an important question. And we also recommend research in action recognition to evaluate models with more domain shift to be reminded of these remaining issues. But coming to the conclusions of the thesis, so we've investigated the recognition of equine pain by learning spatial temporal features from pixels. And in doing so, this has served two purposes, which is to advance the boundaries of automated pain recognition in animals. But we've also studied which deep video models seem suitable when data are scarce and for fine-grained action recognition. And we're also the first to make use of spatial temporal features for pain recognition in animals. We were also early on in presenting empirical studies on what video models learn. And we've opened up to a discussion on the potential shortcomings of very large video models. And throughout our studies, we've focused on, well, emphasized the importance of temporal modeling at a low level and the question of how to model frame dependency. And we've seen that recurrence may be advantageous when a model should be robust to domain shifts. Well, we've also found indications in differences in what models and veterinarians focus on in terms of pain behavior, where the model seems to lay more focus on the movement of the horse and its head position, whereas humans tend to focus on facial expressions based on classical pain scales. And this opens up for possibilities in the future to learn more about horse pain behavior in a data-driven manner. And we saw in the difficult data set with orthopedic pain how necessary it is to have models that can generalize. And since well-labeled data is really difficult to obtain, it's important that models are able to be trained on low amounts of labeled data and then potentially in combination with larger amounts of unlabeled. So then we can say that the empirical properties that we've found in video models are not exhaustive, and the space is really large in which we can compare neural networks. And for one, we haven't studied how pre-training affects the generalization ability of these models. And when it comes to the application, the internal subjective experience of the horses will most likely remain unknown. And for that reason, we can only claim to have detected pain up to some factor of uncertainty. One important avenue that I see for the future is how to make use in an optimal way of small amounts of labeled data together with larger amounts of unlabeled data. I think that's the way to go. And then we have studied horses that have been trained under positive reinforcement to stand quite still outside a box. And of course, it'll be more important in the future to have methods that can operate on horses moving more freely and potentially even outdoors. And last, even if explainability is a growing field, we can still not account fully for the decisions of neural networks. And more precise explainability methods for video models would be impactful for these types of methods. And tying back to the GradCam images that we saw in paper 1, if we could account fully for the classification decisions of video models, we could learn even more from the data about pain behavior. So with that, I'll say thank you so much for listening. And please hit me with any confusions and questions.
Thank you, Sofia.
Thank you.
Do we have some questions from the audience?
Given that it was, really an overview, I know that there are so many things that are.
Yeah, there are many things to ask about.
Yeah.
So this the pain experiment where you actually insert pain in some way. I mean, you talked about some ethical things about that. I suppose you cannot induce above a certain amount of pain, right?
Yeah, exactly. It's always very, in both of these methods. So you saw the blood pressure cuff, the capsaicin, the chili cream on the skin, and then the LPS injection. They're both very regulated in terms of pain level, and it's only moderate pain. Mm-hmm. And the first two ones, they are used on humans as well. Probably the LPS one has been used on humans. I mean, it creates a mild inflammation.
So what happens when the pain is more severe? I suppose experts, veterinarians should have experience with that.
Yeah, that's there's a term called gross pain behavior. When they're in extreme pain, they can like throw their head and kick and things in the box, or even lie on the ground, so show with their whole body that something's wrong.
Okay. But so if you like intuitively, if you train a model on this mild pain, you would not assume it to generalize towards the gross pain then?
No, exactly. That's a good point for the crazier moments, but then it's so apparent for a human expert also that something's wrong, so it's a little bit less needed. So the hope is that these kinds of methods could capture the hours before that something is wrong. And I should say that they're all very regulated, and there have been ethical permissions for all the experiments, and I'm not involved in that. I just get sent the videos. So it's the subtle pain cases that are the most needed to detect. And the big advantage of a video surveillance method is that it can observe the horses during longer time and store information over time, because it's really tedious for a human to observe little muscle twitches and maintain information in our heads over time.
I continue with one question more until someone interrupts me. So for you compared some different models for modeling video.
Yes, I should see if I find that architecture slide that you were. But yeah, go on.
And sort of what do you see? I mean, you had some conclusion about differences of models and what they're good at and what not.
Yeah.
Can you also make some predictions about what will happen in this field in the near term future? What kinds of models will we see in the next 6 months?
Right, for behavior recognition, or for action recognition, or for the animal field more.
I was thinking more about the second half of your presentation, but
yeah,
short.
I love the question, and I mean the field is moving very clearly in the opposite direction from where I would like it to head, because it's moving toward huge video transformers, which can learn.
All other fields.
Yeah, as well. Yeah, exactly, and language and everywhere. So I'm a little, as you have noticed, skeptic toward that. I mean, they can learn. Well, it can work amazingly well for in-domain tasks and to generate images, as we've seen now in the past couple of months. They can memorize pretty much anything and create things from that. But then I think that the fact that we don't really focus on these temporal dependencies and things over time, that makes us not challenge ourselves enough, because we can, I think that requires true generalization that's not captured by these huge millions of parameters models that can memorize YouTube clips. So I think that we will hit a wall at some point, and we'll need to rethink the hardware. Because it's really the GPUs that everything is based on now. That's really mostly allowing for this type of massive parallel computation instead of for recurrent computation as we have in our brains. But I think at some point we might need to align the hardware more with biological brains if we want to achieve sort of true vision. And I should one thing that I didn't mention. So the state of video classification is that we really evaluate on data sets, for example, with different sports or that are really spatially separable, like basketball from golf, or maybe at the most challenging, dribbling from dunking in basketball. And they are both essentially spatially separable. So I think what's needed is to try to classify clips with much more variation and domain shift. That's what if we do that, we'll find out that these huge models have problems to generalize. The way I didn't have an agenda for this when I started. It's just what I've noticed on my strange data. So I believe it to be true that those big ones can't generalize, but maybe some amazing discovery will happen with them too. Who knows? But that's my hypothesis.
Thanks.
And
do we have more questions? We see some applauding Zoom hands.
Okay, how nice.
So I think everyone is happy. And then let's conclude this seminar. Next week, we'll have a visitor from Google Brain, Neil Zegidor, who'll talk about neural audio codecs called Soundstream. So welcome back, September 8th.
Fantastic.
For today.